So we look at a different kind of example which does not involve communications, right. So this is the next example I am going to look at, right, is using, well, as you might expect, right, sooner or later we will have to draw cards out of a hat and flip them, right. We have coins, we have hats, we have dice, so these things we cannot do without, right. So we have to because all the time we might be all electrical engineers here, but we cannot avoid going out of the examples that only interest us, right. We have, so in the spirit of that statement, right, let me look at this example. Consider 3 cards, right. I will call them R, 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 B, B, B in a box, right. R stands for painted blue, red on both sides or something, or marked R on both sides, right. RB is one side R, the other side B, BB is both sides B and B, right. Supposing you take one, you close your eyes, take one card out of the box at random, then throw it in the air, right, just everything with your eyes closed, right. Or somebody does it and you do not get to see what they are doing, right, or I mean assume that the experiment is in fact done randomly, right. Then like a coin, the card also is going to settle with any one side showing exposed, and you do not know what is on the other side, right. You only open your eyes after it has come and it has fallen on the ground, let us say, right. So pick one and toss. One side is exposed, or let me say one face of the card is exposed. So it is obviously the exposed face is going to be either R or B, right, there is no other possibility, right. So supposing R is exposed, what is the probability the other side is B or R? Pick one card and toss, right, one face is exposed. Suppose R shows up. P of other side. So this is given when someone says suppose, that is the conditioning event, right. So this is what we want to analyze. This situation we want to analyze this little more formally rather than just simply informally trying some arguments, right. So we are going to make before we even assign probabilities, we have to write the sample space of the experiment carefully, right, that is the fundamental starting point. So here again we have in all of these cases we will have 2-stage randomness, right, a hidden randomness that selects the state, which you again can't do anything about. Obviously the state here is which of these 3, right, cards you picked, right, and then the observation is which side showed up after being tossed. Then you can make an assumption that given any particular card it is equally likely to show one face or the other, right, that is a standard argument. So therefore drawing this in a way very similar to this, right, again we are not, instead of writing omega in a flattened manner like this, it makes more sense to think of omega with a cause and effect type of diagram, right, rather than linear diagram, right, a linear list, right. So keeping this available to us, we will draw a line here. The nice thing about using this board is you can selectively erase and, right. So having, instead of going back and forth between slides, which is very painful for an observer, right, the board contains a lot more space, right, than a slide. So I will exploit that and draw a diagram here which is similar to this now, except now that we need 3 possibilities, right. So you have RR, RB, BB. Remember again, R is nominally red and B could be any blue or black or whatever you want, which is not red, or brown also, right, anything which is not R, right? This R is the same as this R and this B is the same as this B, okay, right? So that you can't tell by looking at what shows up exactly which card you have drawn, right, obviously. Then, so this is the hidden state, right, this is the state and this is the observation. I was, maybe it's okay, I guess I will have to live with all of these extra fittings here, right. So, so again, right, here we can draw these connections, but some of these connections will have 0 probability. For example, regardless of the prior probability of selecting RR, RB or BB, you cannot get to B from RR. So this is clearly going to be 0. Similarly, from BB you cannot get to R. So that also will be 0. I don't even have to connect the right, do the connections. So this will, all the probability this will be concentrated in that branch. Given that you picked RR, you can only get R. RB, however, tells you that you can go both to R as well as B, and BB you can only go to B, right. So let me write this 0 and then this is 0 here. Okay. So what are now the conditional probabilities? We assume that each of the cards is fair, right, and that when you toss any one of the cards is equally likely to show either face. So therefore, P of R, right, showing up, which I am just going to write as R showing up given RR is 1, P of R given BB is 0. Okay, this is where the half is going to come. So you are going to assume P of R given RB is half. This is the assumption. The fairness, the equally likely option. So you have half here and you have half here. Then what are we going to assume about the input state? Obviously we will assume fairness again, right, and we will assume that they are equally probable, but note that that need not be the case, right. How can you easily have unequal probabilities? All you have to do is have different numbers of the RRs and RBs and BBs, right. Again the very intuitive or way on it's very clear that if you have many more of RBs than you have of RRs or BBs, and obviously you're more likely to pick, assuming that you pick the granularity is at a different level, right. Some card you're picking at random, so if you have 15 cards, well, the probability of picking any one of those 15 cards is 1 by 15, but supposing they are divided unequally, right. So there's a standard way of simulating unequal or actually getting unequal probabilities, right. Very a simple way of for example having coins with unequal probabilities of head, tail and so on. You map it to colors, right. Okay, so but if you assume, okay, it does not matter, we can we'll try to be okay in the case they are equally probable, right. So we will assume that they are equally probable because that's the most important I mean this case, the way in which it's stated in all the literature, right. The most common answer for this, I mean what would you say is the answer here? You all, I'm sure many of you have already worked it out, but if you said half, it's not the right answer. What is the right answer? 1 by 3. That might look counterintuitive, right, but it is. That means that if you see R, you are more likely to have picked RR, right. But anyway, let's do the whole thing out, right. Now I think I can erase this because I have drawn this, so I don't need the same diagram, same kind of diagram here. So let me quickly get rid of this. So P of R are seen or R shows up, for example, as P of now I don't have to put for BB because I know it's not, right, that term will not exist in this right, in this summation because that's 0. So this is basically 1 into 1 into 1 by 3 plus this is RB here, right, this is half to 1 by 3. What is this? Well, it does not matter, you just leave it like this, you do not have to simplify, right. So the most important thing of course is this thing, P of other side equal to B given that R shows up, this is what we want. So what is, how do you simplify this conditional probability? This is the probability that you have picked RB and, I mean the numerator, right, that is the okay, let me first write the first point in English and then we will, so this is R shows up and the other side is B. Divided by probability that R shows up. So what is this numerator? That is, you picked RB and what? R and R has shown up. Both things have to happen. So that's always a subset of the denominator. This conditional probability can never be more than 1, remember. RB picked and R shows divided by probability that R shows. So what is the numerator now? The numerator again you can write as in all our other examples, you can condition on RB being picked. Again this base rule thing, right, it's being so intuitive, right, it's so easy to jump into it and say this must be this given this multiplied by the probability of this, right. What is the probability of R showing up given that you picked RB? It's obviously this term. So half into 1 by 3 divided by 1 by 3 plus half into 1 by 3. So this is why you get what you get, which is what? 1 by 3, right? So if you simplify this you get 1 by 3, isn't it? Wait a minute. Yes, yes, exactly. So I noticed some quizzical looks out there, so I thought even at this point there should be, right, there should be no major problem with this number, right. Earlier you may have thought, well, if I saw if I saw R, I can only get B or R, and by the symmetry of the problem it should be equally likely, but that's not true, right. Okay, so sometimes, right, not sometimes, many times probability will, right, give you what looks to be the case will not end up being the case, right. It will give you some counterintuitive results that you have to watch out for. But you cannot go wrong if you lay out the problem correctly. You start, you don't, you separate out in this case the two-stage randomness, the first, right, the selection of the state and then the observation, right, and then you write out the correct conditional probabilities and so on. It will work no matter what, right. Even if these conditional probabilities are exactly what they are, if these change then these numbers can change obviously, right. Clearly this 0 and this 1, I can add the 1 here now I think, right, this 0 and this 1 are not going to change no matter what. But these numbers can be made to any set of 3 positive numbers between 0 and 1 just by, as I said earlier, by having more cards, more identical cards which rather than just 3. After all, if you can paint one card red and on one side and black on blue, or on the other side, you can paint more than one, right, and so on. So you can create any scenario you know, any setup you want, right, in a very simple way. So if you try to argue this from different and somehow you still got the correct answer, it may not help you, right? If you don't argue systematically, it may not help you in the right in the general situation where the numbers are not exactly right as they are here. Any questions on this? We certainly can have an exchange, camera or not, doesn't matter, right? Please don't hesitate, right? This is a normal lecture just like any other. Once again, let me remind you, right? There need be nothing between us, right? If you have any legitimate question, you should ask, right? Okay. Okay, so let me right, you know, I hope I've convinced you of the utility of this kind of approach, right? And as I said, the same thing, the same mathematics holds, right, in a bunch of situations of this kind, right? The important takeaway is that you should identify the states and observation correctly. If you do that, you can apply, right? Okay, so let me not I don't need this anymore. So let me go on to something else. Okay, so let me make sure. Okay, the next thing I'm going to, before moving on to the different topic, let me look at this conditional probability chain. A chain, right? So if I have given 3 events A, B, C, how do can I write this AP of the joint event A, B, C? When I write this, right, this is the joint probability of observing A, B and C in a particular trial, all 3 of them, right? You are assuming that this joint probability is non-zero, right, that in fact you can observe the 3 events jointly. So this is, let us say, right, one way of simplifying this is to condition on the event AB. So I can condition on AB and get this, C given AB times P of AB. This is exactly by definition, assuming that if ABC is, probability of ABC is non-zero, and probability of AB cannot be 0 either, right? So we are assuming that all the conditioning events have some positive probability, not 0, right? In turn, this P of AB can itself be can be written as P of, let us say, B given A into P of A. It is one way, right? Of course, you can have many other possibilities here. Why should I only write it this way? I can also write it equally well as A given B C or B given C or whatever, right? But starting out like this means I have P of AB coming out here. So therefore, this is P of C given AB times P of B given A times P of A. This is one way, right, of note. This is not the only way, this is one way of writing this conditional probability chain, right. So I have, right, one, the last term is going to be a kind of a prior probability of observing one of those events, the others are all conditional, and you can extend it to more than 3 also. So when does this property become very useful? Let's right, this property becomes very important in the analysis of sequential, you know. Here we had only in the discussion prior to this, we had like two stage randomness, right? If you have more than 2 stage randomness and so on, right, like three successive things happening, right, you can use this to analyze that. So for example, if you have again, I picked this out of one of the, out of Bertseker's, so it seems to be the simplest example of this kind, right? So supposing I have the standard deck of 52 cards, and 3 cards drawn one after the other. Drawn in sequence, right, one after the other, right, without replacement, obviously. When you say in sequence, you don't put anything back, right. So now if somebody asks you what is the probability that none of those 3 cards is a heart, right. In one first draw or second draw or third draw. So this is clearly a joint, right, event exactly like this. So how do you mathematically, right, simplify it using this notation? Clearly you can condition, right, it makes sense, you can start with the first, that's the easiest one to think of. You draw one card, what's the probability that's not a heart, right? Then condition on that. Given that that first card is not a heart, what is the probability that the second one is not going to be a heart? So it turns out that I can't write all that all the stuff on the board, otherwise I'd be reproducing a textbook on the board is not possible. So please associate this first draw with A, the second draw with B, and the third draw with C, right? So therefore this is P of no heart in 1 or 2, no heart in 1 times, that would be P of A, no heart in 1, right? That's the easiest one. You'd proceed only in this sequence. So maybe you can think of this as starting with P of A, then doing this first stage, second stage, third stage, right? So no heart in 2 given, no heart in 1 multiplied by P of no heart, that would be P of, right, B given A. So what would be P of C given AB? It would be no heart in 3 only, given no heart in 1 or 2. I'll just write 1 comma 2 because that's a joint event, right? You're saying no heart either in the first row or second. So now it's easy enough, right, to write out each of these things. So this is clearly what? Given that you have 52 cards and 13 hearts, what's the probability that one card is not going to, assuming that you can pick any card at random, right? The probability that you won't get a heart is what? 39 by 52, exactly, right? So you're picking, right, anything except those 13 cards, or 3 by 4, it doesn't matter, right? This, no heart in 2, given that you've pulled out something which is not a heart, that means you have 51 cards and you have only 38 cards in there, right, which are not hearts. So this second term becomes 38 divided by 51. The third thing is what? 37 divided by 50. Given that you pull out 2 cards which are not both hearts, that means that all 13 hearts are still there in that given, right? And you have only 37 now cards which are not hearts. So 37 divided by 50. This same, right, number can be obtained using combinatorial analysis also, right? Basically it is nothing but 39C choose 3 divided by 52 choose 3, but that I will say for a different lecture because I have to review a little bit of combinatorics, right, for the benefit of those of you that have forgotten that subject, right? We will need some combinatorics in this course, we can't again avoid that, so I'll do it at the right time, right? So I think with these examples I will not do any more examples just on conditional probability. I think I've done enough, right? The whole of in fact today's class we have pretty much devoted to examples, right? So what we're going to take up next is the study of independence, right? And look at how to combine, there are 2 kinds of things that we can talk about, we'll do it tomorrow, right?